before I do this, I was trying to tell you that there's an order structure, right? Order, I would say relation. Order relation in X, where X is some set, okay. I don't, we shall write this as less than or equal to. I use this symbol, but nothing to do with comparing the usual numbers of less than or equal to. This is an abstract notation of less than or equal to. Don't give that meaning. When I say 2 is less than or equal to 3, in that sense 2 is less than 3. It's not in that sense, okay. Some relation it gives you. So that helps you to compare any two elements that you pick from X and then say that X is less than or equal to Y in some sense. If I say X is less than or equal to Y, I put my Y on the right of X, okay. I put my Y on the right of X and say that X is less than or equal to Y, XY in X, okay. Then this is what is called as a relation. I relate X with Y in that sense. If that doesn't happen, then if Y is less than or equal to X, this is not the one that I mean. I'm only looking at this now. So, once you define a relation, what it will give us? Well, okay, if it is your set is set of natural numbers, okay, and then I take my relation less than or equal to the usual less than or equal to relation of comparing natural numbers. I say that whenever I say that X is, then I say that X and Y are comparable. So whenever that happens, then I say that X and Y can be compared in some sense, okay. Another question arises, can we compare all such XYs coming from X? That is one thing. So if I can do this for all XY in X, that is one thing. Can that happen? Okay. If it happens, fine. Otherwise, then we will have to think. That's right. For example, I take my X, Y as two natural numbers, M and N, and then I say that M is less than or equal to N. Okay. For all Mn, if I say, okay, I am setting some order for all Mn. This will happen. Means, how does this order looks like? So this order would look like, so for my M is equals to 1, okay, and now, simple, so, then obviously, there is another thing that let me also say. Obviously, X is less than or equal to X for all X in X. There is no harm. Like A is subset of A for all A, because every set is a subset of itself. So if I use that relation less than or equal to as inclusion, okay, then I can expect that A is a subset of A for all A. So this such relation, what we call it as reflexive relation. It's obvious, quite obvious. Yeah, you want to? Yeah. But if I change A and B, will that happen? That is the problem. I want this to happen to for all. If A is less than or equal to B, will that mean B is also less than or equal to A? That's the question. Okay. If that happens, then such a relation is called a symmetric, isn't it? So that is a stronger for all those things. Now, one thing that we can expect right? So, and then this would happen if A is less than or equal to B and B is less than or equal to C for all A, B, C, then A is less than or equal to C for all. That can happen. If it happens, then we say that this relation is transitive. So, a relation that you define on X satisfying all these three conditions will form a nice relation called as an equivalence relation. So, the relation that you put on X, okay, will become an equivalence relation on this. And then this partitions X into subsets, some class of set, something like that. So, an ordered relation gives a nice structure on the set X. So, for example, we see that natural numbers are ordered in a natural fashion, and this is the order. God given. 1 is less than or equal to 2, 2 is less than or equal to 3, 3 is less than or equal to 4, and all those things. Isn't it? This is not symmetric. We say this is anti-symmetric. Right? If X is less than or equal to Y and Y is less than or equal to X, then it should happen X must be equal to Y. This is what is called as anti-symmetric. So it's not a symmetric, but anti-symmetric relations is reasonably, you can expect such things to happen. So, in such a case, we say that the order is it's not a complete order, it's a partial order. Partial order. An anti-symmetric, transitive and reflexive relation on a set will give you a partial order. And sets with such an order are called as partially ordered sets. So your set of natural numbers are partially ordered sets. You can do that. Okay? Yeah. Now I define again, well, okay, I take some natural number, say 12. I look at its factors, okay, and then I define a relation, okay, in N. I define a relation like this, okay. I look at relation in N now. For M in N, M is less than or equal to N if M divides N. That's my relation. If M divides C, take two numbers. If M and N are those two numbers, M either it can divide N or it need not divide N. These are the only two things can happen. If it divides N, then I say M is less than or equal. They are comparable. Then we say that if M divides N, then M and N are comparable. See, these things have got a lot of applications in theory of automata, computer systems, they proof systems, they generate. Because applications, when you look at applications, common sense is that I know how to apply. My cat doesn't know how to apply. I know it's milk boiling. Okay, machine should know this milk is boiling. That is the whole problem here. So the whole mathematics has to be translated effectively, and then technology will employ that knowledge and then executes the instructions. That is what these things came up. Okay. So, theory of computing in 4 volumes are there. The art of computing, or the art of computing, by everybody should read these 4 books. You cannot take. Donald North from Caltech. All questions are answered, he would say. At the end of his lectures, last lecture will be, the students will sit with him and then they ask questions pertaining to the course that he has given for that semester, and then he says all questions answered. So this is comparable. Now you look at these things. What are the divisors of 12? 2, of course 1, trivial divisor, 3, 4, 6 and 12, including 1 and 12. 1 divides 12, 12 divides 12, 2 divides 12, 3 divides 12, 4 divides 12, 6 divides 12. So 1 divides 12 and therefore both are comparable according to my relation. 2 divides 12, 2 is comparable. Now 1 divides 2, that is comparable. 3 divides 12, 1 divides 3, 2 does not divide 3. Chain is breaking, right? The chain doesn't break in the usual less than or equal to usual less than or equal to relation. The chain continues. Here chain breaks. 4 does not divide 6. Right? And therefore, what is happening here? You draw a lattice diagram, right? Whenever you say that these two are comparable, then you join. You join by what? Because your 2 divides 4, so I put on the head of 2, 4. That's it means. Alright? And now 3 divides 6. I will put this on the head of 3. Now 2 divides 6, 3 divides 6, 4 does not divide 3, and then I join. That's it. Alright? Now 1 divides all, 12. Look at this now. Nice crystal structure has come from this order relation. So this is how these numbers are ordered. God had given in this order. With my handiwork, I put them in this one. Something like, benzene ring, or they talk about it. So it goes like this. So this is lattice diagram. So you can check this for 32, 18. See, if the numbers become bigger and bigger, this problem becomes really challenging. It's very difficult to get all these things. So this order relation that I'm talking will also give me an interesting, say, I have some arithmetic operations I perform, and then maybe I will take this and then order relation. This is interesting. This is if you replace this by x, this is called as a Boolean lattice, right? So I'm x and then they take px, power set of x, and then inclusion, set inclusion, complementation, they do all those things. Your Boolean structure is for a set x, inclusion, complementation, set is structured. All right. Now, if you do this, you try this for n cross n. You try this. I call that as a one-dimensional lattice, Raman. Picture I am giving is on a plane. Now I call this as a two-dimensional lattice. Alright, so take same 12. See what is happening. Check. Check. Three-dimensional. Two-dimensional. Three-dimensional. You can check. Basically, see, what is that? Yeah. X is equals to ABC. What is my power set? Power set has 8 subsets, right? You get a cube. Right? No, this is set inclusion. This less than or equal to is set inclusion. I don't know what really I need to give a meaning for 12 cross 12 cross 2. I'll have to give a meaning to this. I don't. Okay. So this is a very interesting relation, order relation. It sets into a partial order, and then you talk about hey, what is happening here? As I was trying to tell you that 2, 4, 3, 6. So this I can say ground level, level 1. This is level 2. Something like lift, something like this. Okay. They enjoy the same status. They are not comparable. Therefore, I cannot say that in this relation 2 is less than or equal to 3. No. You cannot compare 2 and 3. They are not comparable. If you want to compare, you say them as they are on the same level.
Is it the reason why it's called partial order?
Yeah. That's why it is called partial order. It's quite natural to have antisymmetric relation. Symmetry is, you are expecting too much. X less than or equal to y, y less than or equal to, if and only if x is equal to. Set inclusion is the best one. Equality. See what on number set, equality is obvious, total order, right? But equivalence, that's what Gauss says. Congruence says. Equivalence, not equality. Equality is in absolute sense. X is equals to y, therefore x minus y is equal to 0. But now I want x congruent to y 0, mod 0. X congruent to y should go to 0. So that's what I went in the morning example I gave, even, odd, and all those things. That's it. It divides a set of integers into 2 equivalence classes. Each class representing for even integers, the other one representing for odd integers, with the leader 0 as its principal head, 1 as the principal head for these 2 classes. Their union gives you the whole integers. Nothing is lost. Everything is there, but it is stuck in a nice structured manner. Ellaru horage bardare, ಒಬ್ಬೊಬ್ಬನ ಕರೆದ್ರೆ ek do some NCC order. Ek balne wale.
This is a theorem.
Huh?
If you have an equivalence relation,
Yep.
set S, then S can partition
Into equivalence classes. That's a theorem. Actually, it goes so this figure is commutative. F phi rho. Everything is there. Onto surjection. Onto that. So many things. See, simple facts. Nothing you do. One small start operate division. Division is a very non-trivial operation. Because you have to be careful with zero that appears in the denominator. And therefore, and again, why I drive home the point is that if you try to look at Z modulo 4, things are different. Because 4 is composite. See, prime divisors is one thing. Yeah, Raman was trying to tell this. Candles. Okay. Primes have only 2 divisors. Number of divisors for primes are only 2. One and that itself. If M is composite, this set is non-trivial. All the divisors D such that D divides M. Alright? And therefore, your G modulo 4, this is some system. This is, say, another system. This system is different, this system is different. This system is no zero divisor system, no zero divisor. Here, zero divisors. That's why some people come with, I will prove 1 is equal to 2. My son used to, Appa, I will prove 1 is equal to 2. How? Suppose 1 is equal to 2. If you suppose 1 is equal to 2, you are dividing with 0. 1 is equal to 2 means 1 minus 2 is equal to 0. That cannot happen. You are dividing with 0, this is nonsense. Your arithmetic collapses. And then you arrive at, therefore 1 is not equal to 2. Where you have gone, there is something, they multiply this side, that side, and then you get cancel, 1 is equal to 2. You are actually doing that by zero division. We also did. We went to our teacher and said 1 is equal to 2. Okay. So for calculus, this is very important. Order relation is important for calculus because in the morning, Raman was all the time trying to tell you that because this is a process. Okay. So I want my x. Okay. I want an approximation for root 2. So that's how you get the first Pell equation. The first Pell equation was this. M square minus 2n square is equal to 1. This is a Pell equation. Diphanton equations. Cattle problem. Raman. Then he writes in that, in Arabic, or in Greek, this one. In the heavens of something he writes like this. There were 4 types of cattle. This shade, and then this many were there in this many numbers, 2 times, that many type cows, 3 times, this many, how many were there? So it's a cattle problem, and as a Pell's equation, very nicely given by Lenstra. H.W. Lenstra gave these lectures when I was in US in the year 2000 on algorithmic number theory workshop. Okay, so it's very important for your calculus. Now, because I compare numbers, can I compare functions? Suppose you have function. What is that function? I have my fx, sin x, gx cos x. Some of you, yesterday did you attend Vidyasagar's lecture? You were there? Department end lecture series. He took this example, very interesting examples. He took that one. X real. So f is from R to R. So you plot the graph of this function. Sin 0 is 0. So pi. So I can say 2 pi. Period is 2 pi, right? So I plot the graph. Fundamental period. How does it go? Pi by 2.
It goes to pi 1
and then drops and then comes back. This is one cycle, right? So I bound. So your sine and cos are bounded. What is cos now? Cos 0 is 1. So it should start. So I think it would collapse here and then would how does it go? Something like this. It go. Pardon? Earlier was right. Okay? Something it goes. They traverse different paths. Your computers are there nowadays. You just put it, you will get sine, cos with different colors. You can see those things. Okay? That clearly gives you. You can compare them. So see, f of x naught is the value of this function at x naught, and f of x1 is the value of this function at x1, and therefore I compute those things, and then I keep looking at sine and cos. Okay, and then I compare. I can even do this. I can even do this. I mean, did you get this point? So here, if your cos sits there, sine sits there, sine pi by 2 is 1, cos pi by 2 is 0. So those values I compare. And then say that cos is less than sine or sine is less than cos. For every x. Means what? I'm trying to, obviously by defining f of x is less than or equal to g of x for all x in R, domain of this. If this happens, then I say that my f of x is less than or equal to g of x. Means I am using this order relation to compare these two functions. Alright?
Yeah, in this case you will not be able to do the comparison.
Why?
During one interval, cos seems to be more than sine. During another interval, sine is more than cos.
That's what, whichever way you want to put it.
I feel for some functions we should go by normal.
Not, that's what I said. Absolute value is only I'm taking. This can work. This is an equivalence relation. Yeah.
But sin x and cos are not related
by this relation. That's okay. Any algebraic equation is related. Any algebraic, I'm sorry, any elementary, any algebraic is okay.
These two are not related, but this relation can.
Yeah. This is how you can define integral. You can define integral that way. Okay. So, you must, if you were to look at, so order relation we have put on sets. arithmetic relations we have put, structures I mean, after relation. I put the structures on there, and so and then the concept of limit comes. Then the concept of a limit. Now, I take the example of Raman, that the set unit circle. Okay? I define unit circle like this. I write unit circle as a standard notation S1 unit circle as set of all ordered pairs. I am constructing a set now. Set of all ordered pairs XY, Cartesian product, something like R2, alright, such that x square plus y square is equals to 1. So this is my set now. Right? So I can give its graphic account. 0, 0 origin you take in the Cartesian plane, R2, real plane. So I take 1 on the y-axis, negative x-axis, negative y-axis, and then I draw a circle. All these things. So any point P is xy in R2, okay? And since P is on the circumference of the circle, it satisfies this condition because its distance from the fixed point origin to P is 1, and therefore this point of R2 belongs to S1. Alright? What about if I stretch this to Q? Q is again some x tilde y tilde in R2, but x tilde square plus y tilde square exceeds 1 because the distance from this to this is greater than 1. And therefore your Q will not belong to S1. Ruled out. For similar reason, if I take R, Q do not belong to S1. One becomes the interior point of S1, the other one becomes exterior point of the S1. P is the only point which is the point of S1, which lies on the circumference of the circle. That's how we describe this. So this is my unit circle. Area of this unit circle, my radius is 1 pi r square, therefore the area is pi. Alright? Area of S1 is pi. So area is pi, and then I bring in this Pythagoras theorem. After all, my R2 is a Cartesian plane, therefore I will have to drop a perpendicular from P and M. So this is my X and this is my Y. Alright? So if this is my X and this is my Y, hypotenuse is X square plus Y square, and then this angle that I see is theta. So it's a radius vector. I rotate in the anti-clockwise direction in the xy plane. I describe all the points of S1, okay, as theta varies from 0 to 2 pi. It comes back. That is 1 radian. And again it starts like your dial on the watch. Okay? So when it describes this, we know that parametric representations of x and y from our trigonometry, knowledge of analytical geometry. This is cos theta, r cos theta is, this is sin theta. So your x square plus y square is equal to cos square theta plus sin square theta, that is equal to 1. I am realizing this in some sense. What is happening here? What is happening here is, see, at every time you are trying to scoop this, okay, as theta goes, so you are scooping all this, okay, for infinitesimally small. Or there are two things that can happen here. One is a polygonal triangle and then at arc triangle kind of it. This arc, there are two triangles. That's what you do in calculus. Now when you prove limit of sin theta by theta as theta goes to 0 is equals to 1. That's what exactly we are trying to do there. The concept of limit comes from this geometric information. Okay? So I get n polygonal approximation to your circle. Okay? And so I got a polygon. With n sides. I can keep these sides equal. Okay? All these triangles are isosceles. Because these two sides are radius. They are fixed. So that is fixed. These are all isosceles triangles. Okay? So you cover the whole thing. So for each theta n, theta n in n, I have cos theta n, I have sin theta n. So I get a countable set. From a continuum background, okay, I get into a sort of this. That sort of this is this polygon. So in the bargain, these frills are lost. What is the maximum, what is the minimum that you can lose? I want this. You do Shankar Pole, something like that. You take Shankar Pole, you do this. And then what these people do, they make Shankar Poles, and then again they take back the dough remaining and then put it in the main dough and then go on doing this. I don't know whether they will finish it up everything. I don't know. Last Shankar Pole you will never get. Not possible. So I used to see, nowadays they do these things. This Raman comes, they do all these things because it will be raining outside. No, neither men folk go out, women folk. Well, they go on frying these things. Chakli, undi. then they want some reason. Nagara Panchame. Tan padi how bandirtada hogirtada. Now Panchame ಮಾಡಿಬಿಡು undi. So these are all cultural nice things, you know. That and some people write Kavanas and get Nobel Gnanapita Prashastis also. Panchame Hadu Bukka published. All right. So that's the limit concept you get. So inscribing regular n-gons in a unit circle gives you limiting value. Asymptotically what you get is the unit circle itself. My teacher used to tell this in PUC. I was taught by my teacher in my hometown. Stephen, today I remember that. He used to teach.
And still today also, this is standard example units.
Yeah, they give that. In those days, we never had a set, net, all these things were not there. No engineering. We never went to engineering. We never saw, only 3 or 4 engineering colleges used to be there. We knew that we are not going to be there. Why should we break our head? Aram say, my college I can see from here, go there, sit, and then that's how we could do good mathematics. That's another solace we get. Okay, so what else? Yeah, Yeah. So what is this? The derivative concept. Continuity and derivative. So after limit you start talking about continuity, right? So what is this continuity? So Raman was telling in the morning we have all sorts of functions, right? Functions. All sorts of functions. Let us take polynomials, algebraic function, something. Take polynomials or some simple examples. What are polynomials? Polynomials by definition, some function. I define polynomial on a ring, they say, okay, I will define like this, okay, from R to R, in the spirit of calculus. A n x raised to n, a n or x is an indeterminate or some variable. This is a polynomial defined over R. It's a polynomial. Now, what is, see, without our knowledge, so many things come into picture here. Topology comes without our connectivity. Connectedness comes. See, when I draw a graph of a polynomial, say, for example, if I draw a graph of a polynomial 1 plus 3x only, okay, and then gx, I have 1 plus 5x square. Say, these two polynomials are there, let us say. Okay. When I draw the graph of this function, we know that this graph is linear. It has linear graph. This is quadratic. Okay? And it is curved. Geometry is interesting here. Alright? So I plot the graph of both of those things. Certainly both will not pass through origin. Right? So one goes like this. X is equal to 0. One goes like this, something like this. Alright? So now I compute f of x naught and f of x1 for some x1, x0. Say I will take x0 is equal to 0, x1 is equals to 1. I compute the value of this. My f of x0 is what? 1. Am I right? Yeah. What is f of x1? 4. 1 plus 3 times 1, 4. So where can I plot them? So if this is my 1, somewhere here I have 4, somewhere I have here 4. So f of x0 will be, this is my f of x0, alright, and then my f of x1 is 4, f of x1, alright. So I am coming from x0 to x1 all along this x-axis, and I go all along this y-axis. So as I traverse all along this x0 to x1, x1 minus x0 is the segment, this interval that I get. That is connected. A segment whose length is mod x1 minus x1 connected. Corresponding chunk is mod x1 minus fx0. That's also connected. Right? You pick arbitrarily any point between x0 and x1 and then check that heuristic. I am not doing a rigorous one. F of zeta. So, somewhere here. This is my zeta. This is my f of zeta. Connected. The graph literally doesn't have any breaks. That is continuity. Continuity by perforce gives you the notion of connectedness. If the graph of the function has no breaks, then we say that the function is continuous. This is heuristically we say this. Otherwise you will have to settle down to epsilon delta definition. Otherwise what you will say? Limit f of x as x tends to x naught must be equal to f of x naught, you say. The value of the function at x is equal to x naught. If that happens, then we say that the function is continuous. This is what exactly is your epsilon delta business. Less than epsilon whenever mod x minus x naught is less than delta. So you will never forget this. So epsilon delta function of continuity, both are equivalent. So the analytic expression of continuity is limit concept given for the function, and then calculus is what it says is that this function approaches every value between any two intermediate values, thus chosen arbitrarily, and so that the graph of the function has no breaks. And therefore the function is continuous. Your problem is solved. In verbatim, that will happen with gx also. In verbatim. Because picture says that 1000 words continuous. ನೀವು ರಿಂಗ್ ಹೋದ್ರೆ ನಾವು ಮೇಸ್ಟ್ರಿಗೆ ತಪ್ಪಿಸ್ಕೊಂಡು ಹಂಗೆ ಹೋಗ್ಬಿಡೋದು. ನಮ್ಮ ಮೇಸ್ಟ್ ನೋಡ್ತಿದ್ರು, ಅಲ್ಲಿ ಹೋಗಿದ್ದು ನಿನ್ನೆ ಬರಲಿಲ್ಲ ಕ್ಲಾಸಿಗೆ, ಫುಟ್ಬಾಲ್ ಆಡ್ತಾ ಇದ್ರು. So you can see, that's a better picture. When you, from down, from this, you can see many things happening on the ground level. So, this is the thing. Is that okay? Now, non-trivial situation. All continuous or discontinuous vehicle. Some non-trivial situation is required. Now, what is that non-trivial situation? Any example? Any? Which one? Step function. Very hard for simple step function, right? How do you define step functions? Huh? Screening.
What is the greatest integer function?
That is a post office and also something of that floor value you get, right? Yeah, you can give many such examples for discontinuous functions. So they define in f of x is equals to something thing if x is less than 2, less than 3, and then less than or equal to 3, and then another description, then 3 is less than x, all that, okay? So you will get a discontinuous function. Alright? So there again you will have to check all these things, the values will not match. These limits may exist and all those things, okay? See, there are so many situations. Limit may exist, may not be equal to this. Left hand limit, right hand limit, because this is a oriented space. Real line is oriented one, okay? You have positive sense and negative sense, and therefore you have to talk both the things on those things. But the complex situation is totally different. There is no order in C. So I don't talk all that in C. This is nonsense. There is no order relation on C. I can't compare two complex numbers. If at all I can do, I can take their absolute values, their real numbers. In that case, my C is an isomorphic copy of R2. So you get norm. So if Z is a complex number, then mod Z is the norm. Square root of x square plus y square. So that is complex. We don't do complex calculus and complex at PU. Polytechnic also don't do, right? Because Polytechnic they may be doing. Poly means many. Polymath. Yeah, you must also know what is this types of functions is 1, 1 onto 1, 1 and onto bijections. They are very important things. Bijections, continuous, inverses continuous. See, they are all very, very special type of functions that you will be interested in. Now, when you get into forest, you want to see gorgeous tiger, not again rat, cat, bat. so that's the thing. So, bijections. So, if I have a function from x into y, because you here for a student you talk only r to r, and therefore my inverse is also from R to R again. Alright, I fix my domain and codomain as R, and therefore for f, if I have an inverse, means a function with codomain as a domain, and then domain as codomain for f inverse, then f inverse is the inverse of f. ಅಂದರೆ ಇದು ಉಡುಪಡ್ಡೆ ಅದು ಅಲ್ಲಿಂದ ಇಲ್ಲಿ ನೋಡೋದು ಇಲ್ಲಿತ್ತಲ್ಲ ಇದು. So here I will have to see now. That means I will have to solve this equation 1 plus 3x for x. So what is this? 3x is equals to f. So put to 0. I have to solve this equation. So 3x plus 1 is 0. 3x is minus 1. X is minus 1 upon 3. Right? Am I right? Now define g of x is equals to minus 1 upon 3. That is my inverse. Or 1 plus 3x. Is that okay? Oh, sorry, why? I'm sorry. Why? That's what I was wondering. What you will get? What is the dx? How do you define gx? You will define it as g of x only. G of x. X minus 1 upon 3. Whole divided by 3. Chidanand is okay, right? Okay. I trust you. Okay. Now you compose them, you will get this. What is the property? Group property? F circle G, that is F circle F minus 1 must be equal to I. That is same as F inverse circle F. So you get my inverse also. If your function, see, all continuous functions need not have inverses. See, if everything is fine, no problem. Only bijections have inverse functions. Alright? So, we have bijections, continuous functions, they are inverse functions. See, everything is in place. If you encounter an inverse function, you have the information about the function. Go back to that function, because what is it that you are doing? You are solving a system. This whole thing is a system. It's a mathematical system. Calculus is a system, a mathematical system. The whole idea is, through this mathematical system, I solve the problems. So that is what it means. See, when I say that y is equals to f of x, I am trying to solve for x. That's what it means. Y is equal to f of x means I want x. Like your encryption and decryption. Isn't it? So f minus 1 is actually the decrypting code for f. When you operate this on that, you will get your x. That is the thing. Powerful application. That's why calculus is very powerful. The whole idea is you need to discretize this. That's all. That's of course. Now, computing in reals is a very advanced one. They don't look at even a discrete kind of. If it is a real, fine. Function, I will compute sin x to any accuracy. That's not an issue for x real. So that's the thing. Okay. So what is this differentiability now? Is there anything is there? I think continuity is okay. Left continuous, right continuous. ಎಲ್ಲ ಅಷ್ಟೇ. ಅದೇ ಅಲ್ಲೇ ಗಿರ್ಕಿ ಹೊಡೆಯೋದು ಅಲ್ಲೇ ಅಲ್ಲ ಈ ಕಡೆಗೆ ಇದು ಆದರೆ ಈ ಕಡೆಗೆ ಇದು ನೀವು ಬೇರೆ ನಾವು ಬೇರೆ ಹೀಗೆ ಅಷ್ಟೇ. ಅದು ಕರ್ನಾಟಕ ಮಹಾರಾಷ್ಟ್ರ ಬಾರ್ಡರ್ ಇದ್ದಾಗ ಅವೆಲ್ಲ ಐ ಆಮ್ ನಾಟ್ ಫ್ರಮ್ Belagavi, I am an outsider. I always tell my wife, you fight, I don't want, I want to see you and enjoy the fun. Because this game has no umpires. Because umpires are also players in this. So, what is this, a derivative? You did say something about derivative. You didn't say something about derivative. You said some linear. You said something. So my function is real only. This is something like, this is a stronger version of some calculus concept, derivative. Okay, buy one and get one free kind of a thing will come here. So I have my y, I have my fx. And you should also know these things because we have structured arithmetic. Because you should also see that this as R plus is group, I said vector space, all those things should be there in your mind. Otherwise you cannot add any 2 points here and then you can't scale any point there. So all these things are there in that, okay? And so if I say x in R for small h for small h need not be positive, okay? H in R, h small. You give a translate to push x gently. Okay, so on x axis you have x, so I have pushed x to x plus h. Alright, so correspondingly I have my fx and then push this fx to f plus h. That's what. Now I assume that I am drawing a picture and therefore okay, this is my y is equals to fx. Where should I go? Okay. So I say in this sense, positive sense. Okay? Monotonically increasing. All right? In this positive. Pardon? Is it not correct? Dash dash, okay? ಇಲ್ಲಿ ಬರಬೇಕಾ? Okay. Okay. Yeah, I want some tangent here.
Then write the subscript one.
Right. Yeah. So my x plus h minus fx upon this is what you compute, right? So this reference you take. Again that polygonal story here. To drop this. Okay. So fundamental theorem. Drop these things. So actually, to talk about derivative, you get an integral, and then you talk about derivative. Summation. You get an integral, but in the small, what happens is that you are approximating this curved one by a line segment. This gives you line segment as you make h go to 0. So I want these strips as small as I wish. So in that process, this curved thing disappears, becomes flat. That is derivative. So I quantify geometrically as a line segment. So that is derivative. And if it exists at every point, then I say that the function is differentiable on the whole domain of its definition. All right? So now you take S1. You look at all these things. S1. Differentiate this. We tell students to differentiate this function and all those things. You get very nice things. On the semicircle, you go on drawing the tangents. See, it gives you the turning effect of this particle moving all along the circumference of the circle. So you feel the curvature. Derivative is something to do with geometry. Okay, you quantify that one. So that is a soft option methods available in calculus to compute the volume, area, length, derivative as a rate measurer, all you talk, okay. These are all applications of the derivatives. So the integral comes up in a quite natural because it's an inverse operation, we say in some sense, and therefore we don't have much to give anything there. Of course, it's a challenge that any given function, if it is can we integrate any given function? It's a big question, and that led to so much of research and expanded very vastly in other areas. Okay. So, anything that I can talk? Is it okay? Yeah, I enjoyed giving 2 lectures. I don't know how much you got into these ideas, but anyway, it was a nice experience to me to interact and meet some of my old students, some of my present students, something like your children and our children, my children are playing with our children. Somewhere in Kittur Rani Chennamma PG Center of Dharwad, their children, Rani Chennamma University and our children. And therefore, our children, their children have come together. So it's a very interesting thing to note. Thank you very much. Okay.